Hello everybody, I'm going to talk about spectral flatness and volume of intersections of p-ellipsoids. I am Juhos and this is a joint work with Joshua. A few words concerning the history. Schicht and Schmuck and Schläger have proved that the limit of the Lebesgue volume of intersection of a unit volume p ball with a scaled q ball equals 0 or 1, depending on whether the scaling factor is above or below a certain threshold. Schmuck-Schläger a few years later proved that at the threshold itself, this limit equals 1/2. Kabluchko and Brochner recently have generalized this to Rayleigh balls. So instead of the p power, we have some so-called Rayleigh function, and again there's a threshold behavior. And based on recent results from information-based complexity, we now considered p-ellipsoids instead of p-balls. So p-ellipsoids are defined analogously to p-balls, just with additional semi-axis sigma I. Simple observation is that any p-ellipsoid can be expressed in terms of the corresponding p-ball by a scaling matrix. This also is valid for the unit volume, ellipsoids and balls. And in this fashion, also the volume of intersection of a p-ellipsoid and a scaled q-ellipsoid can be expressed as the volume of the intersection of a p-ball with a scaled q-ellipsoids with proper semi-axis. A bit notation. Boldface sigma always is a triangular array of positive numbers, the rows of which serve as the semi-axis for ellipsoids. We also define the p-Gaussian distribution of the real numbers given by its Lebesgue density. The infinity generous Gaussian distribution is just the uniform distribution on interval -1 to 1. And also we give names to the moments of the p-Gaussian distribution, the exact values of which are not of concern to us now. The first main result consists of the so-called non-critical case. So we take p and q positive numbers. P is allowed to be infinity. We demand that this quantity fq sigma exists, which more or less is a ratio of a geometric mean and an arithmetic mean. And in technical terms, so this is a spectral flatness, which also is in the title of our work. We need some expression to be 0, and this APQ is the same, which also arises in the result of Schicht-Schmuck-Schläger. And then, for all non-negative t, the limit of the volume of the intersection of the p-ball with a scaled q-ellipsoid equals 0 or 1, depending on whether t is below or above a certain threshold, which additionally includes this fq sigma. The second main result is a central limit theorem for a certain q norm. So pq and fq sigma as before. The sigma now also need to satisfy a Noether's condition, which is just a special form of Fellers condition for the central limit theorem. And we need another limit, another number to exist. And then, given a sequence of random vectors Zn distributed uniformly on the p-balls, scaled by some semi-axis, take the q norm and again scale and shift properly, then this converges the distribution towards a centered normal distribution with a known variance, which, because of our assumptions, is not 0. And from this central limit theorem, we can prove the corollary, the critical case. So PQ, FQ sigma, GQ sigma, and S are as before. This HN is more or less the defining sequence for FQ sigma. And we need that scaled with this fraction, it converges to some Z in the extended real numbers. And then the limit of the volume of intersection in this critical case is given by the cumulative distribution function of the standard normal distribution evaluated at minus z over s. Observe that for z equal to 0, this is just 1/2. This is a special case considered by Schmidt. We also have two examples of sequences of some x's which will satisfy the above conditions. The first one is if Sn is eventually periodic, then everything can be calculated explicitly, and this z is 0, so the limiting volume is 1/2. And less trivial, but closer to the applications, if the sigma n, the symmetrics are polynomial in n, then if alpha is above minus 1 over q, then the assumptions for the non-critical case are satisfied. And if alpha is above minus 1 over 2 times q, then also the assumptions for the central limit theorem of the corollary are satisfied. And again, this we get z equal to 0. So here too, this limiting volume of the intersection is 1/2. Only a few words concerning the proofs. A very important tool is a result going back to Schechtner and Zinn concerning the representation of the uniform distribution on the p-ball. So a random vector z is distributed uniformly on the p-ball if and only if it can be written in such a way where u is uniform in the interval from 0 to 1, and the x1 to xn are independent of u and independent among themselves and are p-Gaussian distributed. So, sketch for the proof of theorem A. First, you have to prove a weak law of large numbers for triangular arrays of random variables. Then, rewrite the volume of intersection as a probability involving the q and p norms of this xn. And note that this p norm is more or less a mean of independent random variables. So you may apply the law of large numbers to get convergence towards a constant. And then this will be constant, this will be constant, and so its probability is 0 or 1. For theorem B, more work has to be done. Define this random vector psi n eta n and use a multivariate central limit theorem of Lindeberg to show convergence towards a normal distribution with some regular covariance matrix. And then write this q norm of the scale Zn using this psi n and eta n. Then use Skorohod representation to switch from convergence and distribution to a true convergence. Use Taylor expansion for this last fraction to get rid of second order terms and thus show convergence and distribution for this q norm of z. And then finally, for the critical case, again, rewrite this volume of intersection with random variable as a probability. And then we have our central limit theorem for this q norm. So in the limit, this probability can be expressed as a normal probability, which is precisely what we have claimed. Those are the references. Thank you very much.